Okay, so in today's video, I'm going to talk about kinematic equations. I'm going to show you the four big kinematic equations. We've kind of gone over two of them. And I'm going to show you some alternate forms of these equations, how to use them, and, kind of just what to kind of look out for. Because there are some places where we have to be very careful with what we mean. So, to start, I'm going to start off with this first equation that I gave you. Okay. And I actually want us to be a little bit more exact when we think about this equation, right? Because previously I've been saying distance, displacement, velocity, speed, and I've been really using those things interchangeably, when in fact they're not interchangeable. So in this equation, the D stands for displacement. The V stands for velocity, and the T stands for time. So, in order to use this equation correctly, you actually have to use D as displacement, V as velocity, and T as time, not distance. Okay, and in some of our questions, we'll actually have a velocity that changes, right? Because we have acceleration. So when we have that, this equation is a little bit ambiguous, right? Like, what velocity is this? If our velocity is changing, which velocity should I put in here? And it turns out there's kind of a better form of this equation, which I'm going to give you right now, which looks like this. The displacement is Vf plus V naught divided by 2 times T. And what we're going to see a lot is that in our kinematic equations, in our physics equations in general, we have these subscripts, right? What I've done here is I've added, kind of an F to the modify the V, and a 0, which I said V naught, to modify this V. And all these subscripts do is tell us a little bit about which velocity we're talking about. And, in this case, I'm talking about final velocity. And in this case, I'm talking about initial velocity. And, T is still time, D is still displacement, right? So D is still displacement, and T is still time. Now, before I show you an example, I will mention that this equation only holds for constant acceleration. The good news is that's the only kind of if we have any acceleration in this class, it's going to be constant, meaning acceleration will always, in any one problem, be the same number. It's not going to change. So, if you do go beyond and take more physics, you will learn some different equations here, and you'll find out that this isn't always true. But for constant acceleration, this is actually the correct equation. So how do we use this? Well, in practice, we'll use this in a question like this. So if we say a person walks at a velocity of 10 meters per second to start, Okay, so the question I asked here, a person walks at a velocity of 10 meters per second to start, and then accelerates to a velocity of negative 10 meters over 5 seconds. I'm going to actually change this to what is their displacement? Okay. Well, this is a perfect example of when we would actually use the equation above. So, like any question, we use guess to solve it. So I'm going to go ahead and use guess here. Our givens, right? Initial velocity was 10 meters per second. Final velocity, negative 10 meters per second. Time, 5 seconds. Okay. Our unknown, what is displacement? Our equation, well, we're just using this equation. That was easy. And then substituting in, we have, oops. No, that's correct. Negative 10 plus 10 divided by 2 times 5. And when we solve, well, negative 10 plus 10 is 0. 0 divided by 2 is 0 times 5 is 0. So we have a displacement of 0. Okay. And that is our answer. I chose this question to illustrate not only how to do this, to use this equation in practice, but that it is actually showing us displacement and not distance, right? Clearly this person hasn't walked, a distance of 0 meters, right? Their displacement is 0 because, if we look closely at this question, they started with a positive velocity, ended with the exact same negative velocity. So they've walked, if positive is forward, they've walked the exact same amount forward as they have backward. So they end up with a displacement of 0. But if you were to calculate their distance, you'd have to break this down into 2 different questions. And that is a subject of a different video. So that's our first kinematic equation. The next kinematic equation that I want to go over is the second kinematic equation I gave you in class. So velocity equals acceleration times time. And again, I want to kind of give you a different form here because now we know, well, what velocity are we talking about here, right? We know acceleration. In our questions, acceleration will never change, but what velocity are we really talking about here? And the better form of this equation is going to actually, look like this, which says the final velocity, right, VF, equals the initial velocity plus acceleration times time. Okay, so before, when I was giving you questions, our initial velocity was always 0. And when our initial velocity was always 0, this term canceled out and we had VF or V equals A times T. Now I'm giving you a more general form of this equation where we can't always count on V naught being 0. Okay. So just like in that previous question I gave you, V naught was not 0. In fact, let's go back to this last question, and think about solving for acceleration. So we know that in this question, when this person was walking at a final velocity of negative 10, an initial velocity of 10 meters per second, and they did it over 5 seconds, if instead of asking for the displacement, I was actually asking, well, what is acceleration, right? Well, in this case, the equation is VF equals V naught plus AT. And again, I could substitute in here. Okay, now I actually have to do a little bit of algebra, right? So subtract 10. Okay, and divide by 5. And we get our acceleration is equal to -4. Now, I didn't, follow my units through, but it actually would end up being -4 meters per second squared. Okay, again, units, right? If you need a little bit of help understanding how I do units, that'll be the subject of yet another video. So, if this is really bugging you, how did I get meters per second squared here? Check out my units video. Okay, so that's 2 out of our 4 equations. Okay. I want to go over the last 2 equations here, just briefly. And because this video is getting a little bit long, I'll be making a part 2 where I go a little bit more in depth into these next 2 equations. Okay, so the first of the new equations, right, this third equation I'm going to give you is displacement equals V naught times t plus 1/2 the acceleration times the time squared. Okay, and I'm not going to go into this right now in this video, but in part 2, I'll go into how, what is this equation saying and how do we use it. And the final equation here, or the final kinematic equation I'm going to give you is VF squared equals V naught squared plus 2 times A times D. Okay, remembering that this F just means final, so final velocity squared. The 0 here just means initial, so initial velocity squared. And then the A is acceleration, the D is displacement. So let me go ahead and write the other 2 so you can see this all at once. And we have VF Okay, so these are our 4 big, as it were, kinematic equations, right? We can actually, believe it or not, arrange these equations in a different way. In different ways, we can substitute and combine and come up with other equations, but these 4 are sufficient to solve all of the kinematic problems that we run into in our class. So that's why we call them the big 4 kinematic equations.